In this video, I would like to address how we can handle understanding networks of capacitors that are in series or in parallel with each other. So let's start with capacitors in parallel. Okay, so to remind you what this looks like, I'll just draw a network where I have two capacitors that are in parallel with each other. Okay, and I'm going to name them C1 and C2 so we know which one is which. They could be the same or they could be different. I'm going to allow that they are not the same as each other. Okay, so what we want to do is we want to come up with another capacitor that behaves the same way as this network of capacitors. So I'm going to call that the equivalent capacitor, C equivalent. And what do I mean when I say that it has to behave the same? Well, what I want is when I hook up the equivalent capacitor, instead of this network, I want it to have the same Q and same delta V. So that's the idea. If I have this network of capacitors on the left, or I replace it with the equivalent capacitor, I want to have there be absolutely no distinguishable difference to the rest of the circuit. Okay, so let's start with the delta V. How do we understand what the potential difference is across the capacitor? Well, remember, the two parallel lines on the capacitor represent the different plates. So what I'm going to do is I'm going to figure out what is the potential of one of the wires. Now remember, wires are conductors. And so we have a rule for conductors, which is that wires, which are conductors, have a constant potential. So I'm going to represent that by coloring the wires. All right, so I'm going to color this wire blue. And the whole wire is going to be blue because the entire wire is at whatever potential it is at. All right, so I don't know what it is. I'll just call it V1. But whatever that potential is, I know that the entire wire, everything I've colored blue, has to be the same because our rule for conductors are that they have to be at a constant potential. The same will be true for the other wire. So if I color this green, then the entire wire, everything that is connected to it without anything in between, has to be the same potential. So I'm going to call that V2, whatever it is. Okay, so now if I want to find the potential difference across one of the capacitors, well, I can tell for capacitor 1, it goes from blue to green. So delta V for capacitor 1 is blue to green, because that's how I've colored the wires, which is from V1 to V2. Okay. Well, notice that across C2, the potential difference from the left-hand side to the right-hand side is the same. So delta V for C2 is also V1 to V2. So that's going to be the same. Okay, well, likewise, I told you that I want to have the same delta V for the equivalent capacitor. So that means that I'm going to have V1 on the left, and I'm going to have V2 on the right. Okay, so that tells me that delta V for C equivalent is also V1 to V2. So whatever the difference is between those, that's my delta V. Okay, so the other piece of information I need about capacitance is the charge. So how do I understand what the charge is on the capacitors? Well, if I know the capacitances, they're C1 and they're C2, and I know the delta V, then I can find what the charge is. Okay, so in particular, there's going to be some charge on this capacitor, like this, which remember they're equal and opposite. So this would be plus Q1, and this one will be minus Q1. Meanwhile, this one will have some positive charge and some negative charge. So this will be plus Q2, and this side will be minus Q2. Well, as far as the rest of the circuit is concerned, Q1 and Q2 are going to be coming from that wire on the left, the blue wire. And then Q1 and Q2 are also going to be coming from the wire on the right. All right, so whatever charge I have over here, plus Q equivalent and minus Q equivalent, that has to be the same as Q1 plus Q2. All right, so Q1 plus Q2 equals Q equivalent. The charge is coming from the wire. Whatever current flows down the wire gets stuck as charge on the capacitor, and they have to have this relationship based on the way we drew it. All right, so what I'm going to do is use the definition of capacitance. Q equals C delta V. So I'm going to replace these Q's with C's and delta V's. So Q1 becomes C1 delta V1 plus Q2, which is C2 delta V2, equals Q equivalent, which is C equivalent delta V equivalent. But we already determined that all those delta V's are the same. So since every delta V is the same, I can write this as C1 delta V plus C2 delta V equals C equivalent delta V. And I can then cancel that since they all appear in every term. So I get C1 plus C2 equals C equivalent. All right, and this is specifically for parallel capacitors. All right, so the idea here then is I can take capacitors that are in parallel and I can replace them with an equivalent capacitor, which is much simpler. Instead of having to worry about two capacitors, now I've made them just one capacitor. Okay, so let's do the same thing for the series case. To remind you what that looks like, here's a capacitor, another capacitor, and I want that to have the same Q and delta V as one equivalent capacitor. All right, so again, C1, C2, C equivalent. And there's no reason to think that the relationship should be the same if they're in series, because we have a totally different picture that I've drawn. So what I'm going to do is the same sort of analysis with the delta V. So on the left, I'm going to have some V1, which I'm going to color blue. And I want that to be the same in my equivalent circuit. Okay, and then on the right, I'm going to have some V, which I'm going to call V3, and I want that to be the same. Okay, but in between, I have a different one, V2. Okay, and I don't know what V2 is relative to V1 and V3. It could be halfway in between, or it could be really close to V1 or really close to V3. I simply don't know. But what I do know is that delta V across C1 is going to be from blue to purple. And delta V across C2 is going to be from purple to green. And then delta V across C equivalent is going to be from blue to green, because that's the way that I drew it. All right, so going from blue to purple is some amount, purple to green is some amount, and then blue to green is going to be the sum of those others. So essentially, what I need to work with is the delta V for the equivalent capacitor is equal to delta V for capacitor 1 plus the delta V for capacitor 2. Okay, that's the relationship between those delta V's. Okay, what about the charges? Now this part's a little tricky. So what I want to imagine is, let's say that there is some current that's traveling down this wire. Okay, well, positive charges, let's say, will build up on this side of the capacitor. So that'll be a charge of plus Q. And we know that the way capacitors work is they have the same charge on both sides, just opposite sign, so same magnitude. So this side will have a negative amount of charge, but it'll be the same amount minus Q. Well, that charge flows down the wire. So whatever positive charge left the right-hand side of the capacitor flows away and gets stuck on the other capacitor. So we're going to get plus on each of these. So that's got to be the same amount of charge as we had before, plus Q. And the reason is because that middle wire is neutral. There's no way for additional charge to get onto that wire because there's a gap inside the capacitors. So we know that the minus Q on the left-hand capacitor has to be equal to the plus Q on the right-hand capacitor, no matter what else is going on. I don't need to know anything about the capacitors in order to make the claim that those two have to be equal, because there's nowhere else that charge could have come from. Okay, and then finally we'll have minus Q over here, just so that that is a overall neutral capacitor, and then the same current going down this wire. Okay, so the takeaway from all of that is that Q equivalent equals Q1, which is equal to Q2. All the capacitors have to have the same amount of charge on them. Why is that true for the equivalent case? Well, here I want it to look the same, so the charge is something that you'd be able to detect in the rest of the current. So the charge here, plus Q and minus Q, those have to be the same as it was for the other parts. Okay, so what I'm going to do then is I'm going to take my delta V relationship. So delta V for C equivalent equals delta V for C1 plus delta V for C2. And I'm going to replace those with the formula for capacitance. So remember, delta V is going to be equal to Q over C. So I'm going to make that replacement for each of these. So Q over C equivalent equals Q over C1 plus Q over C2. And I made the case that the charges are all the same. So if I cancel those out, I get 1 over C equivalent equals 1 over C1 plus 1 over C2. Okay, so that's the relationship for capacitors in parallel, or sorry, in series. Okay, so notice that this relationship is different than the other one. So if I solve for C equivalent, then I'm going to have 1 over C1 plus 1 over C2, which I cannot make into just C1 plus C2. That is a different relationship than the one that we had before.